Okay, so this is 6.5, part 2. The graphs of secant and cosecant. We did 6.5, part 1, a little bit over 3 weeks now. That was graphing tangent and cotangent. I know that seems a long time ago, but here we are at 6.5, part 2. Now, make sure you've already done everything from the previous lesson. If you are trying to do this without having fully completed the last lesson, it's going to make your life harder. We're going to be using cosine and sine in order to graph these functions. So you need to understand how to graph the cosine function or the sine function on a Cartesian coordinate plane. This is the way the book teaches it. This is the way a lot of other math teachers teach it. It's going to be a lot easier to think about the graph of secant and cosecant through thinking about the graphs of sine and cosine. Now, I'm going to go ahead and preview what these graphs look like. They kind of look gnarly. So this is the graph of the cosecant of x. Nothing like you've ever seen before, just a bunch of parabolas over and over and over. It's something brand new and something you haven't seen. Just like if we look at the graph of the secant of x, really similar. Those parabolas have shifted their place a little bit, but does not look super pretty. It's just the same parabola over and over, and then the same parabola but negative over and over. So how do we get this? How do we make this happen? And how can we make it so that we can graph these without banging our head against the wall? Well, what I'm actually going to do here is I'm going to think about the fact that cosecant is actually the same thing as 1 over the sine of x. And since it's the same thing as 1 over the sine of x, it also has a period of 2 pi. So for the sine of x, if it takes 2 pi radians for us to start repeating our values over and over, well, that same principle is going to lie with cosecant of x. And that same fact holds true for f of x is equal to the secant of x, which is the exact same thing as 1 over the cosine of x. And since secant of x is the same thing as 1 over the cosine of x, and cosine of x has a period of 2 pi, well then it holds that the secant of x will also take 2 pi radians to start repeating itself. And that will be the cycle of both secant and cosecant. So now we have 4 functions with a period of 2 pi. And those 4 functions is when f of x is equal to the sine of x, the cosine of x, the secant of x, or the cosecant of x. And then we have 2 functions with a period of pi, and that's when f of x is equal to the tangent of x or the cotangent of x. So it's important that we make sure that there are 2 functions in which these periods shift. We look at so many that have a period of 2 pi, it often trips students up to think about the fact that 2 of your functions actually only have a period of pi. So it's something that you want to keep in mind when you're doing these graphs. All right, so here we have the graph of f of x is equal to the cosecant of x, but I've already kind of hinted at this. We're just going to think about the fact that this is 1 over the sine of x. So what I'm actually going to do is I'm going to graph f of x is equal to the sine of x in red. We know where our points are. I'm going to scale this y-axis by 1/2. We already know that I have a point here. I've got a point here. I've got a point here. And I've got a point here. Just like I have a point here. I have a point here. I have a point here. And I have a point here. So then I'm going to go ahead and draw my sinusoidal wave through these points. First thing I can start thinking about is anywhere, if I've got a sine of x that is equal to 0, well, if I've got 1 over 0, that's undefined. So anywhere where I see sine of x being equal to 0, wherever this function crosses the x-axis, I actually have a vertical asymptote. So I go through, and anywhere where I see that sine function cross, well, that means I've got that vertical asymptote. Along with this, I can think about the fact that anywhere where sine of x is equal to 1, well, 1 over 1 is equal to 1. So that means on all of the peaks of this function and on all of the valleys of this function, I actually have another point that just matches up right along with it. So I'm going to go ahead and put that cosecant of x point on the exact same spot I have it for sine. I'm going to do it in blue, though, to represent the fact that that's my cosecant. I'm going to go ahead and erase all of this because this is kind of just extra information to kind of help prove what I'm doing. I'm going to start thinking about the nature of fractions. We know that the sine of pi over 6 is 1/2. So if I did 1 over 1/2, well, that's 1 over 1 times 2 over 1, which is 2. Okay, well, what about, let's think about the sine of pi over 3. Well, that is root 3 over 2. And then that would mean that 1 over root 3 over 2 is equal to 1 over 1 times 2 over root 3. You can plug this in on your calculator, or we could rationalize this again, and you would see the fact that this value is still greater than 1. So the fact that the range for sine, which is something that we learned and reviewed, the range of sine is -1 is less than or equal to y, which is less than or equal to 1. That's the range of sine. So that means every single value of sine is either 1, 0, or some fraction that exists between there. And when you divide 1 by a number smaller than 1, it actually ends up larger. So since we have numbers that end up getting larger, that means as sine gets smaller, cosecant actually gets bigger. So then it creates parabolas that start approaching the vertical asymptotes, and once they get close enough, they just have that asymptotic behavior where they start following along the asymptote forever and ever and just stick with it. Now on the homeworks, this is kind of how my graphs appear. I have the graph of whatever function I'm making the reciprocal of in one color, and then I actually have the graph of that cosecant or secant in a different color, and I denote that on my answer key so you can follow along with it. However, on a test, I would expect you to go through and erase all of the sine graphs because I'm actually concerned with the graph of the cosecant, not of the graph of the sine. And this is actually what the graph of the cosecant looks like. It repeats over and over, and it holds to this cycle. Now, again, let's go down to this Desmos graph of this. I can see here that at 0, pi, and 2 pi, I have undefined points. Pi over 2 and 3 pi over 2 is -1. And then from those points, which I have kind of marked here, they go up and they go down, depending on if we're at the peak of the sine function or at a valley of the sine function. It's written on the table, but you can kind of see that between 2 and 4, so right around 3.14, and right after 6, so right around 6.28, we've got vertical asymptotes that exist, and we're going to see that again at 0. We would see that again at -3.14. This is just what the nature of the cosecant graph does. So there you have it. I always like kind of proving that I don't just make up these mathematic principles as I go along, that you plug them into a graphing application and it'll plug out the exact same thing that I did. So for the properties of the graph of secant, your domain is all values of x where x cannot be equal to 0 plus n pi. And then your range of the function is y is less than or equal to -1 or y is greater than or equal to 1. So this represents the fact that y does not exist between -1 and 1. That's where sine or cosine exist. It just doesn't exist in those points. It starts either getting to be a very, very small negative number after -1, or it gets to be a larger and larger positive number after +1. Again, for the domain, remember with this domain, I write this n pi to represent that it happens over and over and over. I'm not going to spend the time to sit down and write out pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. This represents that at every value of pi plus 0, this graph doesn't exist. All my transformations are based on reciprocals of sine. So I'm less concerned with what I'm actually doing for transformations here, and I'm more concerned with knowing my transformations of my sine function, because that's going to lead me everywhere I need to go. Period is 2 pi. I really don't care much about my amplitude value or my omega value. I care about that when I think about the reciprocal of the sine function, but I'm not going to think about that purely within the cosecant function, so I'm not going to take the time to write that down here. So now let's think about the graph of f of x is equal to the secant of x. Well, this is going to be the same thing as 1 over the cosine of x, which we've already talked about some. So you would guess that if for the cosecant of x, I graphed sine of x first, well, then it would stand to reason that for the secant of x, I'm going to graph the cosine of x first. Again, we'll scale this graph by 1/2. Cosine has that 0.01, pi over 2, 0, pi -1, 3 pi over 2, 0, 2 pi positive 1, as well as negative pi over 2, 0, negative pi -1, negative 3 pi over 2, 0, and negative 2 pi positive 1. I'll go ahead and draw my cosinusoidal wave through these points. Now, I'm not going to go into huge detail on how I would start doing everything, because it's going to have the exact same principles as that cosecant function. So, cosecant, if sine and cosine are highly related, well, that means cosecant and secant are also going to be highly related, and it's going to have all of those exact same concepts. So again, wherever I see a 0, I'm going to go ahead and draw a vertical asymptote. Wherever I see a peak and or a valley of my function, I'm going to go ahead and put another point over those functions. And then, depending on if I'm looking at a peak or a valley, I'm going to make that point either my maximum or my minimum of my parabola, and then draw that parabola towards the vertical asymptotes following asymptotic behavior. And then I can go through and I can erase my cosine function. And there you have it. This is actually what the graph of the secant of x looks like. Let's scroll down to that Desmos example. Again, as you can see in our table, at those pi over 2 and 3 pi over 2 values, they're undefined. We already learned that back in section 6.2, but now we're thinking about it purely related to how it relates with cosine. We've got the point 0, 1, and 2 pi 1, as well as the point pi -1. And then again, we could see that at our pi over 2's, we would have those vertical asymptotes appearing. Now, for the properties of the graph of the secant of x, the domain is going to be slightly different, because this is going to be all values of x, where x cannot be equal to pi over 2 plus n pi. but the range is going to be the exact same. It's going to be y is greater than, is less than or equal to -1, or y is greater than or equal to +1. So for my range, I have y is less than or equal to -1, or y is greater than or equal to +1. And again, my transformations, I'm going to be thinking about the cosine of x. So since I'm thinking about my transformations as f of x is equal to the cosine of x, I'm not super concerned with my amplitude or omega values. That's going to come much more into play when I start thinking about my sine and cosine graphs. My period is still 2 pi. Again, we have that graph. Now finally, this is our last example. I'm going to graph the function f of x is equal to 2 times the cosecant of x. Well, since I'm thinking about 2 times the cosecant of x, I'm actually just going to reciprocalize 2 times the sine of x minus 1. So I'm going to go ahead and graph 2 times the sine of x minus 1 first. Now I showed you this method on my video answer key. I didn't do this on the notes, but as opposed to thinking about this as a vertical shift, I'm actually going to think about a fake x-axis at y is equal to -1. So I'm actually going to go through and we'll scale this by 1 this time. And I'm going to go through and create a fake x-axis at this -1 value. And then this makes my life a little bit easier because graphing this, I'm just going to graph the sine function, but I'm going to use this vertical shift as my new x-axis. So it's still going to intercept at the x-axis, now just this fake x-axis. I've got an amplitude of 2, so that means it goes 2 above that x-axis, comes back to 0, goes 2 below it, comes back to 0. And then I'll work both in the positive and negative direction here. I can go through, draw my sinusoidal wave through that function. Well, now that I've done this, I want to draw my cosecant function. Now, the one thing that is a little bit tricky is the fact that when I do the reciprocal of this, I have to consider the fact that the -1 happens after you take cosecant. And since that -1 happens after the cosecant of x, it's not going to be undefined where it actually crosses 0 here. This is not your undefined. So here, that's not undefined. That's still going to end up being defined. What I actually have to look at is this fake x-axis I've drawn. This is where I have my undefined points of this graph. So now wherever this graph intercepts this fake x-axis, where I'm actually looking at the undefined points. But then again, all I've got to do is draw a point at my peak, and then I'm going to draw an upward parabola. I really only want to see you guys getting this point. There are obviously other defined points of secant or cosecant, which we've learned. But when we're thinking about how to graph it, I just want to think about making it a reciprocal of the sine graph. This shows me a huge understanding of trig and how all of the functions relate together. Again, in my answer key, you're going to see all of my answers with the sine and cosine function. I can't erase it because I have to have pen to show up on those scans. However, this would be what the answer looks like. This is what the actual 2 times the cosecant of x minus 1 is. It's not super difficult if we understand our sine and cosine graph because I'm just basing it on that reciprocal. So I go through, I graph the exact same function. I just replace that cosecant with a sine. And then I'm going to use wherever my new x-axis, that shifted x-axis is for my vertical asymptotes. And then I just match up my maximum or minimum to my peak or valley of my sine or cosine function and then go from there to graph. So since we've already done all the transformations of sine and cosine multiple times, I'm not going to give you any more examples in the notes here. If you do need a couple more examples, feel free to go to the video answer key where I go over a couple of those answers. This is your homework for tonight. Make sure that you're getting it done and you're turning it in. And again, make sure that you're watching the sine or cosine video. As always, email me if you have questions. Let's set up a time to talk so that way we can figure this out together.